transforming logarithmic functions. So just one of the things we show is like a congruence between an exponential function. Okay, and this is an exponential function that we've set equal to something, and then we have a logarithmic function set equal to something. Normally, our exponential function, we might represent it like this. F at x is equal to base of some value x. Okay, and a lot of times we write a number in there for the base. Okay, if we were to transform an exponential function, this gets a little confusing with that letter b, but usually we have a vertical stretch and compression. We'll have a b value here. We'll call that the base. And then maybe they use the letter k for a horizontal stretch and compression. X, do they use c?
C, yeah, that's
Great.
for the outside.
Okay. Oh, c's for the outside. Maybe this is d then? Minus d for a horizontal.
Yes, and then plus c.
Okay, great. And then we'll say plus c. So these are our transformations for an exponential function. Now, exponential function, the notation is just different. The x value lives in like the superscript, and they call it a power. And that's where all of our horizontal stuff happens. These are horizontal stretches and compressions. These are horizontal shifts left and right. These are vertical stretches and compressions, and these are vertical shifts up and down. Okay. Your logarithmic function, let's call it, if we were to write function notation, I might write our original one to look like this. G at x, I get a different value because it's technically a little bit different here, is equal to, we'll use log base, so the b value goes here, and x is here. Now, this is not, that's why, this is not identical to this, okay? Because if you remember, b at x is equal to a, okay? But b to some variable is equal to x. It's equal to a different part. It's actually equal to the exponential part of the equation. So these are slightly different. These two equations here aren't the same, okay? These are slightly different from each other. If I wanted to do and think of these as parent functions, this would be our parent function. You ever heard that term maybe? Yeah. These are the parent functions right here. These are the general transformations. Okay. So our general transformations, if we put g at x, same idea as we have a vertical stretch and compression on the outside. We end up with log of some base, okay? And the base again stays untouched. We'll just leave it as a b. The argument, that's what this part is called. This is known as the argument. This is where you're going to get your k value, okay? And then you have x minus d. So these are horizontal shifts. And then finally, I'll put a second bracket here. This is technically a little to the outside. We have our vertical transformations, up or down. So both of these are general transformations just for different functions. This is our log of a base, and this is our exponential function with a base, okay? So these are slightly different, but the general transformations are to these parent functions, okay? Now, even though that these are equivalent equations, this one and this one are not. Okay, so just keep that in mind. We use x because we're graphing, but these two things are not equivalent to each other. Otherwise, I could have kind of written f at x into this piece here. So one of the things we want to look at is probably graphing this. We'll go up to here. I have graphs. I do have graphs. Okay, so let's turn these off for a second. The very first one is log x. Okay, now I haven't talked about it yet, but there's no base here. And technically log x, its base is the exact same. I'm going to write in y equals, just to do a bit of a proof here, log subscript 10 x. Oh, it's red. It was supposed to go a different color. Cancel. Let's make it purple and dotted. No, dashed. There you go. You can kind of see the red one underneath it now. So if I turn it off, notice those are the same. So anytime there's no base written here, the actual assumption is the invisible number is 10. Okay, so we have base 10 with our log. And if you take a look at this, this is kind of, looks similar to exponential, but you use kind of hugging different axes here. If I were to write in an exponential function of maybe base 10, this is our base 10 exponential function. notice that it has a horizontal asymptote at 0. Okay, and then it just goes up and up and up forever. It has a y-intercept, but there's no x-intercept here. Okay, on our logarithmic function, there's no y-intercept. See, at 0 it says undefined. It does have an x-intercept though, and if you notice, the coordinates are inverted. They're opposites of each other. So really what's happening here, I know I have a lot of other functions written on the side. We'll put a little dotted line here. This is the inverse of the other one. We've just found the inverse to this function here. So this is like flipping it along a 45-degree angle. So that's what's happened at this point. We have, this is the inverse. Now I know why that other thing didn't work. This purple one here is the inverse of the green one here, okay? If they ever ask you on comparing inverses, you can just notice that some key points, we'll go and write them in. Actually, can I write on this part? I can write on this part. Let's write in here. There we go. We're going to make a couple notes here. One of them is that, I'll do this one in red. I don't have a very straight hand. But for, oh my gosh, that's terrible. Let's go back. No, I don't want to do that. There we go. I'll use this. This is a line function. There we go. We have a vertical asymptote for our log. Okay, so if we're talking about the log, we have our log of x. Okay, this has a vertical asymptote at x is equal to 0. That would be the equation. Okay, so it does not touch that piece. If we're talking about, let's go blue. If we're talking about the exponential function, and this would be 10 to the power of x. I guess I should have done it in green because that was green, but this has a horizontal asymptote at y equals 0. So essentially, if you think about these two, they're inverses of each other. We flipped from a horizontal to a vertical asymptote. Okay, this has a y-intercept, this one here, of 0 and 1. If we go back to red, we have an x-intercept at 1 and 0. So you'll see how things flip around. And that's the same idea with the horizontal and vertical asymptotes. We might want to write domain and range to these functions, okay? So let's go back to the exponential. At the exponential, we know that it never, x is never, sorry, not true. Oh, I keep going back on that one. I gotta erase. Y is never equal to 0 in this case, okay? If we look at x, I can go back this way to negative infinity and I can find an x value. And even though this looks like it takes up in that trajectory, it technically goes in the x direction forever also. So if we were to say a domain to this, we'd say the domain is, and I know you guys write it several different ways. This is the element of the real. There are no restrictions to it. So another way might be from negative infinity. Do you guys write it like this notation? Okay. To positive infinity. If we're talking about the range of this function, that's a little different. Y is never equal to 0. And coming down here doesn't exist either. Okay. So if we were to write it in this notation here, y is an element of the real, such that y is greater than 0. It's not equal to 0. It never touches 0, and it never goes below 0. A way that you might write it in this notation is we would write 0, and we will write positive infinity. And we have the curly brackets, because the curly brackets means we're not touching. Correct? Is that how you guys use it? Yeah. Square bracket, if I were to write it like this, that means it would be y is greater than and equal to 0, which is actually untrue for this one. It never actually touches 0, so we'll get rid of that piece. Okay? So then using that same concept for our logarithmic function, because we just have a little bit of an inversion here, our range, that'll be the easier one. We're going to start with our range. Oh, I got the eraser. If we look at the range of this function, we're still going to start with y is the element of the reals such that, well, let's take a look at this log. It clearly goes down forever, and it crosses this x-intercept. And while it looks like it goes in that direction, it technically will go up towards positive infinity forever. So there's actually no restriction on that. So again, if we were to use our bracket inversion, negative infinity to positive infinity would be the range. If we were to say domain, we could say x is an element of the real numbers, such that now there is a restriction on our x values. We can see that it goes this way forever, but we can tell from our vertical asymptote that we talked about right here, x is actually never equal to 0, and it never goes on this side of 0. So in that case, we have x is always greater than 0 in this case. And if we were to write it the other way, we would have 0 to positive infinity, like that. So we've written some domain and range for our somewhat parent functions. The parent functions can change a little because of the bases with the logs, and that's a piece I did want to show you. This is log base 2. It's a little different looking. Vertical asymptotes, horizontal asymptotes, all those pieces are the same, just our base changed, so it has a bit of a different looking curve to it. So just keep that in mind. Depending on what base of our log or the base of our exponential, I could do the exact same thing with base 2. If I were to say, 8, already used h, a at x. Do I have a used a? No, I don't think I have. A at x is equal to 2 to the power of x. Same idea. We have, make it blue. We have a exponential function has a different curve to it because our base is a little different on this one, okay? So let's jump back to this here. So we've looked at those transformations. Uh-oh, not gonna let me do something here. There we go. Okay. So with that being said, we can apply these transformations to these types of functions, okay? We'll note that this gives us stretches for up and down and compressions, and this one gives us transformations, so like full movements up and down. The k value here will give us horizontal stretches and compressions, and the d value will give us horizontal movements to things. The exact same things happen with our logs, just that their curves look a little different. We have a vertical stretch or compression, we have a vertical movement up and down, k gives us a horizontal stretch or compression, and d gives us horizontal movement to the left or to the right. So an example you had here is we're going to write one in. Yours was with a log here. You have y, so instead of function notation they use y, is equal to 3. Oh, let's not use that one because it's got a half in it, yeah. We're going to talk about that decaying function. We'll say -2 log, they give us a base 2 of the log, -1 over 3, x minus 1 plus 4. Okay, so what we're going to do is use some of the knowledge that we have from this question to talk about the transformations of this. So the first thing we really want to do when we're looking at this is isolate what variable represents kind of what letter in our general transformation equation. So our a value here is -2, okay? And I didn't talk about the negative parts, the a and the k, but we'll discuss it. 2, so any value where the a value is greater than 1, we consider it a stretch, okay? Now, the operator is important. If it's negative, so if negative, then there's a flip on the x-axis, okay? So if we do a flip on the x-axis, we can bring that over here and take a look at what that, where'd my Desmos go? There it is. We'll take a picture of this page. Go. And we'll clear this. Close that door. So let's take a look at specifically our log, which is the red one we have here. Okay, if I take this function, copy it, and I'll put it as a y, just because this program reads things. If we do negative, notice that we get a flip on the x-axis. That whole thing flipped over. And then 2 is going to stretch it. It's going to pull it farther upwards. So in this case, it pulls it a little farther downwards because we have that negative flip. But it's the same idea. It's like taking an elastic band from the top and the bottom and stretching it, okay? If we go back here, we can talk about the next piece. We might talk about horizontal stretching and compressing. That would be this value here. Now, for values of a third, this is a horizontal stretch. Okay, so if a k is less than 1, we also get a stretch here. It's stretching it by a factor of 3, so it's going to pull it out times 3. And then again, if negative, that's a flip on just a different axis, the y-axis. So what we'll do is we'll show it on this piece here. We're going to take this original one, move it down, plug it in. Again, we'll call it y. And in this case, we put it in here. So if we say a third, oh, that's not what I wanted. How the heck did that happen? 1 over, oh, it's doing it. Let's do a bracket here. So the program reads it as 1 over, there we go, 3. This is the idea that it's been horizontally stretched, so it's been pulled from the side like an elastic. So it looks like it's gotten thinner that way. And if we were to put a negative to it, it flips it on the other axis, okay? So now the idea is that we're kind of going to build them all together, but that's what each of these two things do. The other two, I think, are a little more straightforward. The -1, this -1 is just going to move our value to the right. So if it's positive, it moves to the right. If it's negative, it moves to the left, just by however many units. So it's going to shift it that way. And then the same thing happens here. If this is positive, it moves up, and if this is negative, it moves down, whatever the absolute value of the units are. So what we can do is we can go back into this. We can start combining these. I'm going to put our negative, so we get another flip there, and then the 2. So we're getting closer to what we had, and I'm going to change our originals. Actually, maybe I'll leave the original just so we can see what happened. And then here, I do got to put a bracket around it because there is a bit of common factoring happening. -1 will shift us to the right. So if we take a look at our current vertical asymptote, we're going to see that it's going to move. -1, it moved to the right 1 unit. So the vertical asymptote is now technically at x equals 1. Okay, and then here we said we're going to add 4. The whole thing is going to shift up 4 units. So it's moving up 4 units from where it was before. So this is a very different looking graph. In fact, it looks like it's exponential now, but that's because of all the flips and compressions that we've done to this, and mainly the flips. We've done 2 flips. It almost looks like it's an exponential function instead.